is a PhD student at the ETH in Zurich in the group of Sebastian Huber. Well, the summary of CV will be short because he's still his career is in progress, but he's progressing quite well. So Valerio got his bachelor at the University of Mailand, and then he moved to Zurich for the master. And after the master, he started, as I mentioned now, a few seconds ago, that he started his PhD in the group of Sebastian Huber, where he's doing a lot of experiments probing with classical systems of several topological phases. And today he's going to give a talk about a recent achievement by his group, by him and his colleagues, about the probing of the topological phase in acoustic systems. So Sebastian, the stage is yours. Valerio, sorry.
Absolutely fine. There are similarities. So thank you very much. Thank you very much for having me here. It's actually a great pleasure to have the chance to show you our latest result. Of course, it would be nicer if I could afterwards enjoy a glass of wine on the beach in San Sebastian, but okay, time is what it is. So I'm happy to have the chance to present the results online. So please do interrupt me at any time. I'll try to be as clear as I can, but maybe sometimes I will fail, and please do not let me go on. Please interrupt me and let's try to clarify things.
Yeah, sorry, Valerio. So if you want to make any question, please raise your hand or write it in the chat. And if you want, I can give you the permission to make directly your question, or I can make it for you by reading it from the chat. Please, Valerio.
Thanks. Okay, then let's start right away. So today, as the title suggests, I would like you to show our latest result in the study of another kind of topological insulator, dubbed fragile topological insulator. So let me just try to give you an overview of what I'd like to show you. I would like to start introducing the idea of fragile topology. I don't know if it's familiar to everyone, most likely no. And then starting from that, I would like to convince you that despite the name might make it appear a bit less attractive, fragile topology actually has some very robust signature that might play an important role in a variety of platforms. And if I did my task properly, and I didn't lose you along the way, by the end of the talk, these are the two plots that you should be able to understand. These are the key results of today's talk. And I really hope that by the end of the talk, they become clear and they'll stay with you in your memory for a bit longer than this seminar. So let's start right away with trying to define fragile topology. And I want to start from a rather abstract point of view, because in physics, this idea of fragile topology is rather new. But for mathematicians, it's something very familiar. And I hope also to most of you, because most likely during your studies, you've heard about the hairy-ball theorem. So the hairy-ball theorem just tells you that if you have a coconut and you try to comb the hair of the coconut, you will not manage, you have a singularity. Meaning, if you start from S2, a sphere, and you want to define on each point of S2 a vector field that lives in the tangent space of the sphere, you will not manage to do it everywhere. You will have some points where your vector field vanishes, so we'll have some singularities. And that's just because the tangent space of the sphere is topological. So in this sense, we have topology. We cannot define our vector field continuously, but there is a but, because if instead of the tangent space, we consider the normal space of the sphere, so we allow our vector field to stick out of the sphere, of course, we have no obstruction. We have no problem. We can define our vector field everywhere because the normal space is trivial. So on one hand, we have the tangent space that is topological, and on the other hand, we have the normal space that is trivial. So where does fragile topology comes in? It's when you join the two. So it means when you take your topological space, the tangent space, and you combine it with a normal one, a trivial one, then if you do so, and you define your vector field, it doesn't need to live only in the tangent space, but it can stick out of the sphere. So the moment you combine your tangent space with the normal space, you end up in a trivial space. So where is the fragility? You start with something topological, you add something trivial, you end up with something completely trivial. So it's fragile because your topology is not robust to the addition of trivial, in this case, trivial manifolds. So you can remove this topological obstruction. So that was a rather high-level description of fragile topology. That's what mathematicians would call stably trivial. So they take the other kind of approach. But let's try to see how fragile topology comes into play in physical systems. So there is the magic word topology. So in some sense, we expect to have a topological, in this case, topological insulator. What does it mean? So often you will hear the topological insulator of edge states. That's often true, not always. It's a quite restrictive characterization. What I would like to define as topological insulator is something that is not adiabatically connected to an atomic limit. Meaning you start with your insulator, so you have a system with an energetic gap and some symmetries, and you cannot describe your system in terms of exponentially localized linear function. So you cannot localize all the electrons in your model, for example. That, what for me is a topological insulator, is an obstruction to define an atomic limit. And of course, the fragile topological insulator has this property. Otherwise, we would not call it topological. So where does the fragility comes in is if you add something trivial, exactly as in the example of the Heribold theorem. So if you, in your system, you add some trivial orbital, meaning some well-localized, exponentially localized orbitals, then your system as a whole, with these additional degrees of freedom, is trivial, meaning you can localize it fully. So again, the fragility of this topology comes as it's not stable under the addition of trivial degrees of freedom. So you start with topology, you add something trivial, you end up with something trivial. And I would like to stress the difference with other kind of topology that we are more used to. For example, take a Chern insulator. The only way to get rid of a Chern insulator is to add another Chern band with the opposite Chern number. So the only way to get rid of the topology of the Chern insulator is by adding something topological of the opposite sign. So topology plus topology can give something trivial. But if you add a trivial band to a Chern band, you will always have a Chern number that is non-zero. Here is completely different. Topological plus trivial can be trivial. So that's the essence of fragile topology. So now we set up fragile topology in the framework of a physical system, but it's still a not too useful definition, because if you come from your simulation or from your experiment and you see your band structure, it's hard to establish whether it's fragile topological by adding degrees of freedom. You usually don't have this extra knob in your experiment or in your simulation. So given my band structure, how do I know whether I have a fragile topological insulator or not? And maybe there is no need to explain it here because actually the world expert are here in San Sebastian, but the essence is that for fragile topology, you need crystalline symmetries. So time reversal symmetry, chiral symmetry, particle symmetry, those are not enough. You need to add crystalline symmetry. So you need some symmetries that, for example, here, let's take the example of C4, of P4MM. You have a space group that has a rotation of 90 degrees, a rotation of 880 degrees, and some mirrors. So the first thing you need to do is identify the space group of your system. And just for concreteness here, we take P4MM. And then that's a real space. You go to momentum space, you have your Brillouin zone, and you have some special points in it where you have high symmetry. So what you want to do is you have your band structure from simulation or experiment, and you know the irreducible representation realized by your bands at high symmetry point. So you know how your electronic field, or you will see your wave field, transform under the group, under the symmetries of the point group at, for example, gamma point, M point, and X point. And this is something you usually have access in your simulation for sure, and sometimes also in your experiments. So you have the concept of the notion of all the symmetry properties of your band structure at high symmetry points. So that's your starting point, and now you want to understand whether your insulator is fragile topological or not. And the trick is to reverse the question, meaning don't ask yourself whether it's topological, ask yourself whether it's trivial, because trivial is simpler. Trivial just means that your band structure can be described by exponentially localized orbitals. So you can take your unit cell, for example, like here on the left, you can place some well-defined orbitals, exponentially localized, in this case an s orbital, and then you can ask yourself, okay, what happens in momentum space? What kind of band structure do I have? And in particular, how does my band structure transform under the symmetry of the group at the high symmetry point? And if I place, for example, s orbital here at this particular location, I will have a band structure transform like this. If I put pz orbitals, px, py orbitals, I get a different band structure with different symmetry properties. And the trick, so this goes under the idea of topological quantum chemistry, the trick is that you can do it for all space group and all possible orbitals at high symmetry position. Luckily, you don't have to do it all the time again. Luckily, there were kind people that did it for you and put it on a crystallographic Bilbao server you can easily access online. So what you would do, you have your system with a well-defined space group, and you go online, you check these huge tables for the relevant space group. And this tables tells you, let me place an orbital at one particular position. This label 1b, 1b to c. Which orbital, some other weird labels, A1, A2, that just specify what symmetry has this orbital at that location. And then the data you have is the irreducible representation realized by your orbitals in momentum space at the high symmetry points. So all it's left for you to do is a matching exercise, meaning you take your band structure and you go checking. So I have gamma 4 and gamma 1 at the gamma point, x3, x4 at x, and m5 at m. Can I reconstruct this band structure as a simple sum with positive coefficient of these columns? If I can, then my insulator is trivial. Why? Because it's a simple sum of exponentially localized orbitals. So let's do this task for this particular band structure. We try, and you can try very hard. Hopefully the talk is on YouTube, so you can go back, pause it, and try even harder, but you will not succeed if you allow only for positive coefficient. You will if you allow for negative coefficients. Meaning, let's take the two elementary band representation, that's how they're called when they're induced from localized orbitals. Let's take them with a plus, and let's take the red box with a minus. Then at gamma, I will have gamma 1 plus gamma 3 plus gamma 4 minus gamma 3. So gamma 1 plus gamma 4. Perfect. Then I repeat the exercise at m and at x, and you will see that actually it matches. So your complicated band structure that you get from your experiment or your simulation, in this case, can be written as the sum of two trivial insulators minus a trivial insulator. And it looks a bit weird. All this decomposition is telling you is that you cannot obtain this band structure just by combining atomic insulator, trivial atomic insulator. So in this sense, it's not trivial. It has to be topological. But this weird minus coefficient actually tells you something more. It tells you that if you come to your system and add these trivial orbitals, these B2 orbitals at 1a, then all of your system can be written as a sum of atomic trivial insulator. So that's where the fragility comes in. Fragility comes because if I add an orbital, I can write my whole system as a trivial insulator. Whereas if I don't add this orbital, I have something topological. So this randomly chosen band structure is a good example of two bands that together display fragile topology. So we did one step further. We first define fragile topology, then we look at what it is in physical system, and now we also know how to tell whether the system we are studying is a fragile topological insulator or not. But so far, it's a lot of chatting. It sounds a bit weird. It might be just a theoretical dream. So the natural question that follows up is, can we actually measure it? Can we actually see a system that displays the fragile topology? And as Dario said, I did a lot of experiments, but at heart, I remain a theoretician. So I'm not too comfortable working with electronic materials and old kind of measurement like ARPES or STM. What we do is something, if you want, simpler. We take classical systems and particular mechanical system with elastic waves or acoustic waves. So we don't start with the Schrödinger equation as in this slide. Our starting point is actually the simple Newton classical equation. So we don't have an Hamiltonian, but we have a dynamical matrix. It's a second order equation or the first order equation. But as always, you can map it back to a first order differential equation. And then you can write it in a form that resembles the Schrödinger equation, where your Hamiltonian is actually replaced, if you want, by the square root of the dynamical matrix. All to say that systems are a bit different. We don't deal with electrons, we deal with classical waves. And we classify an object as a bit different, but the idea is always the same. You start with a periodic system, and you study the mapping from your Brillouin zone to the occupied states. Other important difference is that, first of all, we don't have a Fermi level. These are not fermions. So we can explore the whole band structure by changing the frequency of excitation. And the other important property, that this time is a minus for this platform, is that we don't have spins. We don't have spin-orbit coupling, so we cannot have a spin full-time reversal symmetry. And that, as we will see, it's actually important for topological insulators. By now, it's actually rather established platforms, not only by us. This is our work, but worldwide, many people employ classical platforms to simulate topological phenomena. We deal mainly with the elastic and acoustic waves. I include in this macro platform also a lot of photonic platform and photonic crystals. So we used, for example, elastic waves to probe a high-order topological insulator where you don't have edge modes, but your excitation is localized at the corner of your sample. We instead use acoustic waves to implement novel gauge field in wire system in 3D. And you see, this slide is not just to brag, but to actually show two main differences among the two platforms and two main reasons why we do this kind of experiments. On the left, you see this higher order topological insulator that was done with elastic wave. And you see the LIGO figure here helps you getting an idea of the scales. It's not microscopic, but it's not even enormous. It's on the small scale. And elasticity actually has a benefit that, if you want, is a bit closer to real world application, because it could be useful in platforms where you want low dissipative environments. And for example, they could be used in commercially viable mobile phone, where you want both cheap and energetically efficient. Of course, this higher order topological insulator has not been employed so far in any real world application, but there is a hope for that. The acoustic side, on the other hand, is a bit different. These samples here are enormous. They're definitely macroscopic. And here it's a bit also simpler to design, because acoustic is a longitudinal wave, while elastic is a tensorial wave. So it's much easier to design a metamaterial in acoustic. And for us, that's the platform to go when we really want to study novel phenomena. So something that has never been observed before, that we can easily design and measure. Since it's so microscopic, it's also easy to measure. All of this just to argue why in the following we look at acoustic metamaterials. So metamaterials, where what we study is the acoustic waves, pressure waves propagating in a periodic structure. And that is the platform we chose to try to study this fragile topology. So let's go at it. This is the model we chose. There is an interesting backstory why we chose this model, but I just want to stress that we could have chosen any other model. Why do I say this? Because fragile topology is a novel concept, but actually, if you look closer, it has been around for a while. Because in these classical platforms, where you don't have spins, you don't have spin-full time reversal symmetry, it's really difficult to engineer a strong topological insulator like it would be the Z2 topological insulator like K-Melee or ETHzürich. Without spin-full time reversal symmetry, that's not possible. So without spin-full time reversal symmetry, if you look closely at your system, very often what has been labeled as topological insulator in these classical platforms, it turns out it's actually a fragile topological insulator. And there are many examples in the literature, but now I just want to focus on our example, on our experimental realization. So you see, this one here on the left is our unit cell, or it's really the unit cell. So here it's made of plastic, but just for you to understand. But this is where the air wave will propagate. And you see there are some bigger cavities. These would be essentially your orbitals in an electronic language. And then there are small channels connecting these cavities. These would be the hopping. And you see the size of the cavities and the size of the hopping are not so different. It's not a stark difference between the two. So it's not really close to a tight binding limit. It's more a free electron limit if you want. But these to identify the main player, we have the cavities. These are where we expect our orbitals to be, and the hopping channels. We're just connecting these cavities. And you see it's just a bilayer lib lattice with some chiral coupling connecting the two layers. So that's the unit cell. Then you 3D print the whole sample. And mind you, now the sample is the negative of the unit cell on the left, because the plastic will provide the hard boundary of the structure in which the pressure wave will propagate. And you see, again, not exactly an experiment with application in mind, because here the LIGO figure gives you an idea of how big this sample is. It's really a macroscopic sample built with the purpose to show the feature of fragile topology rather than an application in mind. And then what you do, you have your sample, you can just go and measure it. Go and measure it here. It's again rather simple, no need of complicated setups. You just put a speaker at some location. Here you put a speaker here at the center of the sample. And then you go measuring. And go measuring here means you come with a stick with a microphone on top, and you enter with a microphone and measure at each lattice site of your crystal. So you really can do a full bulk spectroscopy of your system. It's a bit of like theory dreams because you have the full information, the full spectroscopic information. So you can then Fourier transform your signal and get the band structure. And that's where acoustic plays a bit less nicely because sounds in air at ambient temperature is lossy. That's why you cannot hear your parents or your friends shouting from the other room. Acoustic is very lossy, and this is the proof. Forget about the white line on top, the color map below is really the Fourier transform of our pressure field. What you can do still is go look at each momentum cut and try to fit the maximum with Lorentzian to actually localize well where your bands sit. So you can determine the frequency of your bands, and then you can compare it also to simulation, and you find out that your experiment matches well your expectation. You have a full gap in the bulk. That's good because we want to study topological insulators. But there is something more. You see in this figure, there are not just the bands fitted to their maxima, but there are also some labels. There are those labels that appear before when we show a simulated band structure. There is this gamma 1, gamma 4, gamma 3, gamma 2, and so on. And these labels are not input from simulation. These labels are actually entirely extracted from experimental data. And so you have now a full experimental band structure with its symmetry property, and you can now repeat the matching exercise you did before, check whether it's a trivial insulator or not. You do the exercise, and you get exactly the composition we looked at before. So you get exactly the composition that you expected for a fragile topological insulator.
Yeah. We have a question from Ingmar Sparta.
Yeah.
Ingmar, go ahead with a question if you want. Sorry. Now you can talk, Ingmar. Maybe. Ingmar, you are promoted to panelist, so if you want to make a question, please go ahead.
Perfect. Yeah. So thanks. So I just maybe a very naive question, but you mentioned that you extracted the symmetry labels from the points from the experiment. How do you do that actually?
That will come exactly in the next slide. So it's going to be perfect. Your question comes with the perfect timing. No, it's great. That's absolutely the right question to ask. I'm telling you I have labels. You need to question whether I'm bullshitting you or actually I can show you that we get it from experimental data, and that's what we'll do.
We have a second question, if you want to take it, by ETHzürich.
Yeah.
ETHzürich, you are promoted now to panelist. You can make your question.
All right. So it was actually also related to the question that was just asked. So I will wait until I see the next slide.
Great. Then a lot of expectation build up now for the next slide. So let's go straight to it. How do we get the symmetry label from experimental data? That's rather simple actually. So we have our pressure field. If we transform it, so let's take just one layer of the bilayer Lib lattice. And this is our unit cell, right? So let's look at one mirror symmetry for simplicity. What's the action of this mirror? It maps the sublattice C to sublattice B and keeps A sublattice where it is. So that's in this sublattice space, that's the action of this mirror. And of course, if we transform each sublattice individually to not mix the different phases, so we can really sandwich our pressure field with the matrix operation to get the eigenvalues of this symmetry. It will not exactly be quantized because of symmetry imperfection, but you will obtain the symmetry eigenvalue for this pressure field. Of course, you have it across frequency, so that's why it's important that you evaluate it at the frequency where you locate the maximum of your response, of your acoustic response. So we check what is this frequency, and then we compute the expectation value of the matrix operator at the frequency of the mode. And then we get plus or minus 1. Good thing is that you can determine it at the whole asymmetry point. Then here you say, okay, you have M5, that's a doubly degenerate symmetry representation. How do you distinguish the two? You take advantage of all the high symmetry lines. In the high symmetry lines, you have mirrors, so you can take advantage of compatibility relations, also nicely grouped in the Bilbao crystallographic server, and then you can really fully characterize the symmetry properties of your band structure, and then conclude it's fragile topological. So that's probably a great time to see exactly. Perfect. The question remains, so let's take it.
We have still a question by ETHzürich. Etzal, please go ahead.
Okay, 1 second. So the question is quite simple. Your objects were three-dimensional, and the waves, I assume, are three-dimensional as well. And so, but then the symmetry analysis that you perform looks to me as if it would be two-dimensional. So how do you solve for that, or what am I losing?
So the system is actually two-dimensional. So okay, there is 2 bilayers, so you can say it's quasi 2D, but still, when you construct your symmetry matrix here, now here, for clarity purpose, I cheated a bit, I consider only 1 layer, but you actually have the 2 layers. So for example, some mirrors mix the 2 layers, and then this would not be diagonal in the layer space, but you would have an off-diagonal component. So that's how you cover the bilayer structure. And then we are dealing with acoustics. So it's actually a longitudinal wave, not a tensorial wave. So that's why it's so simple. Would you have an elastic waves, then it would be much more complicated, because then you would need to disentangle the off-plane motion to the in-plane motion, and then your symmetry representation would be much more complicated. So in a sense here, we are helped by the fact that acoustic is a longitudinal wave.
Okay, fair enough. Maybe we can talk later. But...
Okay, but the moment you don't have a longitudinal wave, it's much, much more complicated.
Okay.
But it's 1D, right? It's a 1D propagating wave. It's in 2D plus format. Okay. So let's assume that we agreed on how we extract our symmetry, then we would have a characterization only from experimental data of our band structure that established the fragile topology of our sample. That's great. That could be by itself a demonstration of a fragile topological insulator. It's a bit underwhelming if you compare it to other topological insulator, where you always show these nice edge states, you always show a spectral signature. So the question is there anything in the spectrum of fragile topological insulator? Is there something in their energy bands that I can take advantage of, maybe even for an application, like I would do with the edge states of a strong topological insulator? And the question at first is a bit sad, meaning, first of all, it's a crystalline topological insulator. So as all crystalline topological insulator, you don't expect robust edge mode at the boundary of the sample unless the boundary preserves the protecting symmetry, which is a rather rare case. On top of that, fragile topological insulator do not come with robust edge mode. So even if you have an edge mode, you can actually gap it out by preserving the symmetry of your system. So edge mode is not the way to go. So let's look for something different that is associated to the spectrum of these systems. And to do that, we need to take a bit of a detour to define some new quantities that I hopefully manage to define in a comprehensible way, such that then we can discuss the spectral symmetry. So what we want to do is associate a new topological index to this system that we can then take advantage of to characterize this spectrum. So let's start with the simplest situation possible. Take 2 orbitals, these are just the 2 spherical objects in this plot here, and couple them with a hopping parameter, the yellow connecting line. So the Hamiltonian is as simple as it gets. You just couple these 2 states, eigenenergy plus minus t. The important thing at the eigenstate, you have 2 eigenstates, of course, and let's imagine inversion symmetry with respect to the center of the bond connecting the 2 objects. One state will be odd and the other state will be even. So I really have the 2 eigenstates that have different symmetry with respect to the inversion symmetry with respect to the center. So now I want to do a little trick. I want to start twisting this hopping parameter, meaning I do a cut line across the hopping and I multiply the hopping term t with a parameter lambda. So my Hamiltonian changes, gets a factor lambda, my energy change, get a factor lambda. And now I want to tune lambda from +1, so the bare system, to lambda -1, where I twist the hopping essentially. So I first start bare system, disconnected orbitals, twisted systems. And what happens is that the energy changes as a function of lambda, of course. It would be linear, it's drawn just for illustrative purposes. But the interesting fact is that at first I had the odd state as the lowest state. Let's imagine half filling. My ground state would be odd. And as I do the twisting procedure, I change the symmetry content of my ground state. So at lambda is equal to 1, the lowest state will be odd under inversion symmetry, while at lambda equal to -1, the lowest state will be even under inversion symmetry. So I change the symmetry content of the low-lying states of my system. I go from odd state to even state. And the only way I can do this is that from my lowest band, an odd state needs to flow to the upper band. And from the upper band, I need to acquire an even state. So somewhere during my twisting procedure, I need to have a gap closing where the even and odd state intersect each other. And the gap closure across this twisting procedure is protected because the two states have opposite inversion symmetry, if I respect the symmetry across the twisting procedure. So what's this twisting procedure? It's just a gauge transformation, okay? So you're just going from h to lambda to h minus lambda. To go there, you just multiply all the states on the right with minus, all the states on the left with plus. So at lambda equal to +1 and lambda equal to -1, you just have the same spectrum because they're related by gauge transformation. But this gauge transformation V actually anti-commutes with your inversion symmetry. So it changes the character of your states under inversion. So if you start with an odd state, you need to end with an even state. And the only way for this to happen is that the odd state flows from the upper band to the lower band and vice versa.
Valerio, we have another question by Edsel.
Yeah, absolutely.
Edsel, go ahead.
1 second. So what's the meaning of a -1 hop in an acoustic system? I mean, what do you mean when you say that you twist the thing? What happens to the eigenvector, let's say, or what happens to the, yeah.
The magic is that, as we'll explain later, I won't take a negative hopping. So there is a trick, but let's go later. But actually you can. It's very simple, meaning let's imagine an acoustic cavity, a rectangular acoustic cavity. Let's take 2, and let's consider a PZ orbital, meaning an orbital, a mode with a node in the middle.
Okay.
Now, if I couple the two cavities on the same side, I get one hopping sign, plus, minus, I don't care. But if I now couple the opposite side, you see the hopping has a different phase relation. Here is plus, plus, and here is plus, minus. So these two hoppings will have opposite sign.
Okay.
That's just a way to engineer coupling of different sign in acoustic or elastic or any other platform.
Okay.
It's just the phase content of the mode.
Okay.
So it's doable. It requires a bit of design cleverness. So if you can avoid it, you avoid it, and we will see. We will avoid it.
Okay.
So what we said is that during this twisting procedure, what matters is that even state turns into odd and odd state turns into even. So what I want to define is an index that tells me exactly what's the imbalance between odd and even state in my system. So let's take again the half filling. So only one state is filled. And let's start at lambda equal to 1. I have only one odd state filled. So my index delta is equal to +1. Now let's go scan with lambda. At lambda equal to -1, I only have an even state field. So delta is equal to -1. My index changed sign. And now it's a bit more long to show that this index is actually topological. But you know that if a topological index changes sign or changes its value, you need to have a gap closure in between. So to convince yourself it's topological, I strongly advise you to go read the theoretical paper that came with our experimental realization. But for now, believe me, this is a topological index. The fact that it changes sign requires a gap closing transition. So what I expect to see is that I tune lambda from 1 to -1, my system closes the gap and then reopens. That's a spectral signature. That's exactly what I wanted to find for my fragile topological insulator. Two important things to notice. I need to respect the protecting symmetry across this change, otherwise this gap is not protected. So this twisting procedure needs to be, for example, in this case, C2 symmetric. And to define a gauge transformation, I need to have a well-defined left and right, meaning I need to have orbitals only at the left and orbitals only at the right. I cannot have orbitals sitting exactly where I cut. These are the two important observations. Now, the second thing is, how do I actually compute this index in my system? Of course, I could just measure all the states of the band, all the states of my system, and figure out whether I have the same number of even and odd states. That's a bit unpractical. It would be nicer if there is a way to determine this index from the band structure. And there is a way. Let's try to argue why. And the easiest way to argue why is actually to start from a real space sample, and actually a sample that has nothing, so a vacuum system. And let's slowly construct our system step by step. So we bring in occupied orbitals in steps, but we want to do it while preserving C2 symmetry, the protecting symmetry. So we always need to bring always at least two orbitals together. And these orbitals need to transform under each other under inversion symmetry, but you're enlarging the Hilbert space. So all of this to tell you that when you bring these two orbitals together, they need to form a balanced representation of C2, meaning they will give you an even state and an odd state every time you bring these two together. So you bring two more, even plus odd, two more, and you construct like this the whole sample in a C2 symmetric way. So all in all, if you construct your sample like this, you will have exactly the same number of even and the same number of odd states. So your index, topological index, is 0. The only way to have a non-zero topological index is to have an orbital sitting at the symmetry center. Because if I put an orbital at the symmetry center, this transforms back into itself. So it doesn't need to come with a balanced even plus odd representation. It can be either even or either odd. So if I have an orbital at the symmetry center, then I can have an imbalance of even and odd state. Why is it important to determine our index? Because now I can look at my band structure. And it's the composition in terms of EBRs, of atomic limit. And you see, my band actually comes from an orbital localizer 1b, that would be here, two orbitals localizer 2c, minus one orbital localizer 1a. So all I care to determine my index is only the orbital sitting at the symmetry center. So I only care about those sitting at 1a. So I only care about this B2 orbital. And from that, I can determine that my index is 1. Why? Because I have B2 is actually even under C2. So I have minus one even state under C2. That gives me an index delta is equal to 1. Another important thing, I told you that my band structure comes from orbital at 1b and 2c minus orbital at 1a. This means I don't have a physical orbital, in my case, a physical acoustic cavities at the symmetry center. So it's exactly the situation I need to be able to cut through the symmetry center, because would I have a real physical orbital there, I wouldn't be able to do it. So what I need is a fragile topological insulator where the missing orbital, the missing acoustic cavities, comes from the symmetry center of my sample. These are all, luckily, ingredients that we have in this platform, so we can do this proposal. So what do we expect to see? We expect an insulator, so a band below the gap, a bulk band above the gap, and a twisting T of some openings across this C2 symmetric cut. And since we have an index delta equal to 1, that is non-zero, we expect that as we tune lambda, as an even state will come from the above band to the below band. And then as we further tune lambda from 0 to -1, an odd state will have to flow from the lower band to the upper band, such that I start with delta equal to 1, and I end up with delta equal to -1. As been discussed already, what does it mean for, can I do it in an experiment? Can I actually multiply my hoppings with lambda from 1 to -1? And as I hopefully convinced you, you actually could, but it's a bit hard, especially with lower acoustic mode. You need modes with a node and you need to play with resonances. So if you could avoid it, it would be better. And the answer is that you can avoid it, because h at lambda, so when lambda is equal to lambda values between 1 and 0, is actually related to h at minus lambda. And the relation is exactly the gauge transformation that relates lambda equal to 1 and lambda equal to -1. So whatever you observe in the region lambda between 1 and 0, you're ensured by this gauge transformation that exactly the same will happen from 0 to -1. So if I see a mode going from the upper band to the lower band between 1 and 0, then I'm guaranteed that the mode with opposite symmetry under C2 will flow from the lower band to the upper band in the rest of the twist. So we have all we need, we just need to do it in the experiment. All we need to do is multiplying our hopping parameter along the cut with the parameter lambda. What does it mean? In type binding, we will do the hopping needs to decrease its intensity as a function of lambda. In acoustic here, our hopping are disconnecting channels for the acoustic cavities. And of course, the hopping that mediates is proportional to the volume of the channel. If you get a big channel, you will mediate a strong coupling, small channel, weak coupling. So what you do to twist the hopping is to insert a small obstruction into the channel. You see here is this C2 symmetric cut. And there is zoom in of the cut. And on the left, you have these small barriers inside the channel. This small barrier obstructs the channel, so it changes the strength of the hopping, if you want, in an electronic language. Now you need to twist, so you need to vary this lambda. So what you do, you take your sample and you 3D print many different versions of this central cut. And these different versions, they only change by the size of the obstruction. So you will start with a central structure that has no barrier, so hopping equal to lambda equal to 1. And then you will tune, increasing the size of the barrier until you get a barrier that occupies the whole channel, that is the fully disconnected 2/2 of the sample. That's lambda equal to 0. So you can do the whole twisting from 1 to 0 just by changing the size of this barrier. And as you do it, of course, you scan the symmetry center of your sample, where you expect the state to flow from even to odd and to odd to even, and you measure the response of your sample there at the symmetry center. And as you do, here you're changing the optimal multiplication factor, meaning you're changing the size of this obstruction. And you see there are modes exactly at the symmetry center that flows from the above band to the lower band. So this is really the spectral signature that we were looking for in this fragile topological insulator, where in the bulk spectrum, you see actually a mode crossing the gap as you perform this twisting procedure.
Valerio, sorry, I have a question myself. So now the obstruction, if I think to this two lib lattice bilayer, is within the same layer or within the two layers?
Right. So the cut goes through the whole thing. It needs to go through the whole sample. So you really need to multiply all the hoppings from the left side to the right side with a factor lambda, right? So this obstruction is only in the upper channel. Why? Because what matters is really the overall coupling between left and right boundary.
Okay.
So the choice of this obstruction is actually motivated by simulation. So we simulate what kind of coupling we mediate among the two structures and what kind of size of obstruction we need to put to achieve this lambda parameter. And the truth is that the chiral coupling here, already for a hopping multiplication of 40%, they're fully obstructed. So it turns out that most of the tuning of lambda is actually done by the in-layer coupling rather than the out-layer coupling. But the physical size of the obstruction to map into the lambda needs to be chosen carefully. Especially, I'm not claiming we do a linear interpolation between lambda equal to 1 and lambda equal to 0, but for sure we move from a strong lambda to a weak lambda. Okay. Nor a linear interpolation is necessary. That's a handy feature.
Thanks.
But yes, you need to fully, like for lambda equal to 0, for example, the full sample needs to be cut, not only layer to layer. So in this sense, we are a bit happy now. We have a spectral signature. It's not edge modes, but we have something in the spectrum that we can associate to fragile topology. It's actually a very well localized mode with very well defined properties under inversion. So it's actually something possibly useful. But still, yeah.
Sorry, Valerio, let me interrupt you again. Could you go one slide back, please? Yeah, this one with the simple, where you see the line. Yeah.
Okay.
Yeah. So now basically on the bottom of the sample, where is the full obstruction? On the bottom or on the top? Or does not matter?
The obstruction is through the whole line. So you see, this is the central unit cell that divides the sample into two parts.
Yes.
I cannot cut straight, but I need to cut in situ symmetric way. So I need to go from the left to the right.
Sure.
And the whole line has this small obstruction along the line.
So to say, on the bottom or on the top, you have no obstruction, and while you are approaching the center, you are obstructing the coupling. Is this the spirit?
So I go here. I go. It's a simple sample.
Okay.
No obstruction. Here I hit my obstruction. In going from left to right.
Okay, but I'm asking top bottom.
Top bottom layer, you mean?
No. If I go from the LIGO to the top.
Here it's fully clean.
Yeah, but if I move okay, clear. Sorry. If I move the LIGO on the yellow line,
yes,
I'm moving from left to right, but the strength of the obstruction, how is changing along the line?
Good point. Fully constant. Along the cut, the obstruction is the same. So it's really one cut as one value of obstruction, so one value of lambda. Then to do a different lambda, I fully remove the central part and I need to insert a new part with different kind of obstruction. But the sample is here, it's really situ symmetric. So this obstruction here needs to be equal to the one here. Otherwise, I will break my C2 symmetry.
Okay, so this means that when I see the next slide, and when I see this plot with different lambda, is this within the same sample, or you have to build up a sample for each lambda?
A central piece of the sample for each lambda.
Okay, so this was completely unclear to me so far.
That's exactly why it has different colors if you want. So what you do when you change lambda, you take away this piece of your sample and you insert a new one where the size of this obstruction changes.
Okay, thanks for this clarification.
So each lambda values is, if you want, a new sample. Yes, that's a very good point. Yeah, there are two more questions. I think that's actually a good time to take questions.
Yes, I start from Magdalena. Yeah. Magdalena, please go ahead. Once you are a panelist, go ahead. Unmute yourself, please.
Okay, thank you. My question is there anything special about those modes which are in gap? Are they localized, extended? Have some
yes, they're very localized at the symmetry center. These states need to be localized in the symmetry center because that's the only state that can allow you to have an imbalance between even and odd state. So they're very well localized in the symmetry center. In particular, would they be a single mode, they would have a well-defined C2 property, meaning it would be C2 odd or C2 even. So that's the ideal sample, that's the dream. Now we are close to the dream, but we're not exactly living in the dream. So our sample has some technicalities that we can discuss later, where when you do this twisting, you actually carry this mode and many other modes. So it's not an isolated mode, nor we would have a way to tell whether it's a single mode or not. What you can do, for example, when you simulate it, is computing the symmetry properties of your modes. And you will see there is only one mode, the one well localized at the center and not delocalized on the cut, that has well-defined symmetry properties. All the other come in an equal balance of even and odd. Only that state will be either fully even or fully odd. So you can actually detect it by measuring at which value of lambda the occupied state change their real space index. So when the imbalance of even versus odd states changes in the occupied state, or states below the gap in this case.
Thanks.
Okay. Can I ask a question?
Sure.
Okay. So,
sorry, I was muted.
Yeah, no, don't worry. So I think I missed something in the introduction of your talk. Why do you need the twisting? So why do you need to go from right to left while you scan the yellow line?
Okay, let's see. So by twisting, I mean just lambda going from 1 to -1. So that's the only twisting. This I don't call twisting. This is just because just to be clear, we're talking about the same issue. This is just to be C2 symmetric. So imagine I could do, for example, I could do a straight line here, right? Going through the center. But then I have a problem because you remember it's a Lieb lattice. So the straight line would cut through this part here. And here I have actually an acoustic cavity. So in electronic, I will be cutting through an orbital. And if I cut through an orbital, I cannot well define what's left and what's right. I cannot multiply my orbitals on the left by -1, and meaning I cannot do the gauge transformation. So my Hamiltonian at lambda equal to 1 and Hamiltonian at lambda equal to -1 would not be identical. So C2 line would be straight, C2 symmetric line straight would satisfy it, but it's not okay because I cut through acoustic cavities. So what do? I cut only through acoustic channels, so I need to decide either I move from the left or to the right of this central cavity. And I need to do it in a C2 symmetric way. So at the bottom of the sample, I say, okay, I move to the left of it. And that's why I only pinch off this coupling channel, not acoustic cavities. Now, on the bottom, I move to the left. If I want to do C2 symmetric, it means on the top, I need to move on the right. That's why I need to use this S-shaped cut to avoid cutting through any acoustic cavities and still be C2 symmetric. So, and here in the center, you see where I cross. I actually cross here. So where I have really just a plastic, no acoustic cavity. That's the symmetry center of your problem.
Okay, beautiful. And then the yellow line indicates where your obstructions are physically.
Exactly, where these where these channels are obstructed. Exactly.
Okay.
And why does it need to be symmetric? Because that's the symmetry that protects the crossing between the user and node state.
That's right. Okay, thank you so much.
I think we're running a bit long, Maria.
No, I think we're fine. We're making
Okay.
well.
Then I go on.
Let's say within how many slides do you have more?
At your pleasure.
Oh, okay, probably we try to keep within maximum 1 hour 5. So you have
oh yeah, sure.
10 minutes more.
Yeah, absolutely. So that's great. I'm happy that we had so many questions, and I hope there will be more afterwards. Usually people are more interested in electrons than classical simulating platforms, but it's great to see so much interest. But I could see somebody raising the question, why? Okay, good. You gave me a spectral signature of fragile topology, but it's something very tailored to engineer platforms where I have this huge freedom where I can insert new samples, I can insert abstraction, I can play with my waves, I can measure the whole bulk. So it's something very tailored to engineer structure. It's a bit harder to see how to do it in electronic materials. Maybe in some 2D materials, you could cleverly gate it such that you realize this twisting procedure, but it's very hard to see there. So if I'm a person fully and only interested in electronic system, what do I care about fragile topology? Is there anything that fragile topology does for my electrons? There's something that I can measure besides the non-localizing my electrons. And it turns out that actually it's exactly the fact that your electrons cannot be localized that might make fragile topology very important also in electronic systems. And the golden standard examples is twisted Ballet graphene. Okay, twisted Ballet graphene got rightfully so a lot of attention lately. And for me, the interesting aspect is the interplay between the single particle physics and the many-body physics in the system. Meaning, on one hand, you have the band structure of the single particle that are very interesting. Actually, the flat bands of twisted Ballet graphene per valley display exactly the fragile topology we're discussing here. And then on the other hand, you observe some very interesting many-body states like a superconductor close to a correlated insulator and all correlated insulator at integer filling. And the question that came to not only my mind, but to the mind of many people is there any relation between this single particle physics and the many-body states? And the aspect I focus my attention is a very narrow one, is the superconducting state, because we're discussing about the superconductor in a flat band system. And in 2D. And in 2D, phase fluctuations are extremely important to establish robust superconductivity. So you don't just want your Cooper pair, your electrons to pair up in a Cooper pair, but you also want them to be coherent. And the coherence is captured by the superfluid weight, just the proportionality between the supercurrent and the gauge potential. But if you do a naive approximation and you compute fast your superfluid weight, you find that it's inversely proportional to the effective mass of your band structure. And in a flat band, the effective mass goes to infinity. So if you just do a back of the envelope calculation, you would expect that the superfluid weight in the flat band systems goes to 0. So no coherent superconductor in a flat band. And that's a bit at odds with what they observe in experiments. So where is the solution of this conundrum? Actually, you can do your calculation more carefully, starting from a Meanfield approximation with the BCS Hamiltonian. So you get your free energy, take the derivative with respect to the gauge potential to compute the superfluid weight. And you find that already at the Meanfield level, there is not just the spherical Cow approximation with the effective mass, but your single particle physics gives an additional contribution. And this additional contribution is geometric in origin. It just tells you how well can you localize your orbitals in your band structure. That's exactly where we expect topology to come and help us, because we said that topology means that I cannot localize my electrons. And if I cannot localize my electrons, it means I will get a non-zero contribution to my superfluid weight. So the question seems settled, but it's settled in the Meanfield regime. And you might ask, how reliable is a Meanfield approximation in a system that lacks a well-defined Fermi surface? So what we wanted to investigate is whether this is at all stable beyond Meanfield. So when you go beyond weak field coupling and you consider a strong coupling system, whether all of these survive. So we took a simple toy model. We didn't want to deal with full glory twisted Ballet graphene. We just took a modified Kagome lattice. The interesting fact of this system, it has two completely flat bands in the low energy state. So these are two fully degenerate, fully flat bands. And these bands have the same topology that we expect from the two flat bands per valley of twisted Ballet graphene. Meaning they have fragile topology protected by C2T symmetry. You can associate to them an Euler class, which is the counterpart of the Chern number. So it's a great toy model if you want. And then on top of that, we added an attractive Hubbard interaction. So we don't question where does the glue for your electrons come from. Let's just say it's there. Once I pair up my electrons, are they coherent? That's the question we want to address. And to do so, we restored to numerical simulation. We did exactly quantum Monte Carlo simulation with auxiliary field method. And that's great because you can really extract the superfluid wave from your system. And you get what you were hoping for, meaning at high temperature, your superfluid stiffness is 0. So you have no superconductor. Then as you decrease temperature, it rises, until at very low temperature, it actually hits this dashed line. And this dashed line is the jump that you would expect in the superfluid weight at the Berezinski-Kosterlitz-Towles transition. And that's the relevant one for 2D because anyway, phase fluctuation dominates. So this superfluid weight obtained from quantum Monte Carlo for very strong interactions actually shows you that your system turns superconducting even beyond the mean field approximation in a full glory many-body system. So you do have a coherent superconductor in 2D. In this system with fragile topology in the flat bands. Moreover, actually superfluid weight saturates beyond the mean field value. So it seems that this bound obtained in the mean field regime in terms of this Euler class, which again is just a counterpart for fragile bands of the Chern number, actually survives the strong interaction and is valid beyond mean field. Good, could be accidental. Does it really mean that fragile topology helped us here in establishing a coherent superconductor? So you can take advantage of the main property of fragile topology to prove that, meaning you can consider adding trivial orbitals, simple s orbital to your system, and try to get rid of the topological obstruction. So in this case, we can add an s orbital here and couple to all the other orbitals of our system. And then we end up with 3 flat bands in the lowest state that are now trivial. You turn on the Hubbard interaction, you go measure the superfluid weight, and it stays very low up to very low temperature. So you got rid of the superconducting state just by coupling a trivial degrees of freedom to your system. Whereas if you add a trivial degrees of freedom that does not remove the topological obstruction, your superfluid weight remains strong and your system turns superconducting. So by getting rid of the topology, by adding trivial degrees of freedom, we got rid of the superconducting state. So this, in a sense, proves the important role played by fragile topology in ensuring a coherent superconductor in 2D for flat band systems. So in this sense, fragile topology seems to be important, not just for engineering system, where, again, I want to stress it's really abundant. Essentially, most of the engineer system, classical engineering system realized to date displays some flavor of fragile topology, not all, but most. But it's also extremely important in electronic system, even strongly interacting one, where the topological nature of it helps you in not having localized electrons and then gives rise, for, in this case, to interesting superconducting state, but it actually helps you also from some excitonic phases of matter. So it has the benefit of the full glory topological obstruction, plus the interesting quirks that it is actually fragile. So you can actually get rid of it by tunnel coupling extra orbitals. And with this, I hope I show you why I'm so interested in fragile topology, despite the name. And it's an interesting and strong signature that you can observe both in the spectra of engineering structure and in the many-body feature of correlating materials. I would like to thank all the nice collaborators that made this project possible, scattered all over the world. It was a pleasure to work with them, in particular with Sadie and Andrea, that provided a lot of input. And thank all of you for your nice invitation, for your attention, and for the very interesting question that came, and I hope will still come in the question session. Thank you very much.
Thank you, Valerio. So it's now open for question. ETHzürich, you can go ahead now.
Okay, now, so I have 2 very different questions. So first of all, your talk was amazing. So congratulations, because you did an excellent job at explaining something that I couldn't understand after reading the article several times. So
that just means I did a poor job in writing the article, but yeah.
No, but I mean, with the animations and all of that, I mean, it's easier to get the point, and with your explanation, of course. So, well, my questions are 2. First of all, when you were talking about superconductors, you said that or I understood that the key for the contribution to this coherence and in the superfluid way was the delocalization of the electrons. And so I wonder if fragile topology is so special in comparison with some other topological effects that you can get in matter in general.
So at least in the Meanfield level, it seems that the contribution comes indeed from the spreading and actually also beyond Meanfield. And no, in this sense, fragile topology is no special at all. Meaning, if you would have a churn band, cannot be fully flat, but a nearly flat churn band, then you get the same effect. Okay. In particular, you don't really need topology. If you have an OAL, for example, so the obstructive atomic limit, then your Vannier function cannot be tightly localized on a single site. It has a finite spreading, and you can actually already use that. The only, actually, in this case, fragile topology, maybe it's not only a benefit, it has actually some deficit, meaning you need to be careful that you don't tunnel couple some additional orbitals and get rid of the structure in a superconducting state. That's, for example, well, it's a bit different, but align twisted barrier graphene with HPN, then you break C2, which is actually, in this case, the protecting symmetry of this fragile topology, and boom, the people seem to not be able to observe the superconducting state. Okay. So in this sense, you need to be careful whether you have it or not, whether you preserve the symmetry of your topology, or in more generic terms, as you said, the obstruction to localize your orbitals, not really a topology.
Well, I guess the good thing would be that you can also potentially control the superconductive material by adding something or remove something. I mean, potentially meaning that, of course, it would be very difficult.
It might not be the most easy tunable knob, but yes, it's one that is available.
Okay. And then my second question is about classical waves, let's say, in these sort of systems. As you probably know, we work with photonics mainly, or I do work with photonics. And so I wonder if you have envisioned any real applications for fragile topological systems in classical waves, because there are no H states, the visualization of the fragility is super complicated. So I don't know.
I don't want to be the party pooper, but I actually take the opposite approach, meaning I'm fully into it. I love this field of topological effects in classical materials. But often, and I'm guilty myself, the application route is very much stressed, more than just the simulating route. And people made those sort of claims, like especially concerning the edge states of these topological classical metamaterials. What my message is more is a word of caution, meaning you might have edge states. They might be there because you carefully tune your platforms and you have this huge degree of freedom where you can make them as robust as you want. But people need to be careful because these are not the edge states of a Z2 topological insulator protected by fermionic time reversal symmetry. If you carefully check what is protecting symmetry is if it's a crystalline symmetry, then anyway your edge states are not so robust, and without spin orbit, they are most likely fragile. Or you need to be honest and say that you carefully engineer a symmetry that it's as if you had a time reversal fermionic system. And why do I say that we are guilty ourselves? Let me go to this slide. Probably most of you know this pendula experiment. That was the first experiment that we did in our lab with the pendula, and that was a simulation of a quantum spinol insulator. And that is true, because there you carefully engineer one symmetry, meaning you see you have always two pendula coming together. This is the unit cell, you have two different pendula, X and Y. And if these two pendula are identical, then you can construct a local symmetry that maps the X pendula to the Y pendula. And this together with the bosonic time reversal symmetry gives you an effective time reversal symmetry that squares to -1. So if you carefully engineer your platforms and you have this symmetry, then you can describe your edge state as a Z2 topological insulator. But what we did in the supplementary of these works was actually, okay, let's say that we break this symmetry between the two pendula. So we don't have anymore a t squared into -1. We are left only with crystalline symmetry, and in this case with C2 symmetry. And you look at the band structure, and surprise, surprise, it's actually a fragile topological insulator. So what you do, you can, now, I was not allowed by my boss to actually go and cut the pendula, because that's a piece of museum in our lab. So I could only do simulation, but if you do in simulation a cut through the pendula, you exactly say the same physics. This is lambda going from 1 to -1, a state odd and a state even flowing. So I don't want to say that the pendula are fragile. The pendula are a good mimic of quantum spinel effect because we have this composite symmetry. But if you don't have this composite symmetry, they're fragile. So when we design these classical metamaterials, we need to be, if you want to realize application for these edge states, we need to be careful in designing some clever symmetry, some local symmetry that mimics a fermionic time reversal symmetry.
And so then, if I am understanding you correctly, if we would have, let's say, a composite or a synthetic, let's say, symmetry, right, like mimicking the fermionic time reversal symmetry, then the fragile system would behave as a C2 system, basically presenting edge states, etc.
You would keep the strongest characterization you have, right?
Okay, perfect.
Because, like, for example, the KMLA model, you can describe it in terms of the Z2 time reversal index, or you could do a topological quantum chemistry analysis and show that it's actually C6 protected. But if you have T squared into -1, it's local, it's stronger, so you keep the strongest classification.
Yeah.
And if you're a purist, and they can give you a hard time, because then you say, okay, in this pendula system, both are individual symmetry. So both the bosonic time reversal symmetry and the engineer local symmetry, they're individual symmetry.
Okay.
So rather than choosing the composite symmetry, you should first go in the eigensector of one and then of the other.
Okay.
You can discuss with the purist, then you would be a fragile topological insulator.
Excellent. Well, thank you so much. Thank you so much for the talk and for answering to the questions.
So, thanks. That's all. Do we have more questions? Well, I have a question myself regarding the idea of looking the effect of fragile bands for a superconducting systems. Okay, you mentioned that already if you pair your bilayer system with a boron nitride, you lose the superconductivity. But probably, sorry?
If you align it, if it's aligned such that you break C2.
Okay, but I mean, could be that any other imperfection along the system are leading to a loss of the fragile phase. I mean, in principle, the lattice along the moire started to relax, to strain, and you depart very fast from the hexagonal symmetry. Absolutely.
I think the question is far from settled. And so there are many proposals. I mean, if it's a phonon-based or it's an electron-based superconductor, there is this proposal by the Wisniewski group where the pairing actually takes advantage of this C2T symmetry and the fragile topology to pair up skirmions. Whether that's the pairing or not, I'm absolutely not entitled to say. My message here is that either you have relaxation effects and then or correlation effect that normalize strongly the single particle band, and then it becomes non-flat, and then you can get coherence just by a curvature.
Okay.
But if you really have flat bands, the only way you get coherence is from non-localized Vannier states. And intuitively it makes sense, because imagine you have this flat band, you project the interaction on the flat bands, so you're left with hopping Vannier states. And if they overlap, they can have a hopping, so the Vannier states can go around. If they don't overlap, so they're tightly localized, you have no hopping for the Vannier states. That's why you want the non-localized Vannier states in your flat band.
Okay, thanks.
But yes, no, how much these actually...
Well, clearly, your model works well for your decorated Kagome lattice. But
exactly. The moment you introduce real-world twisted bigraphene, I think the answer is still far to come.
Okay, great. I will stop the recording now. And well, if anybody, do you have more questions for Valerio, or we can stop the session here? So the talk will be available on YouTube. We have again a question from Magdalena. I will promote you, Magdalena. Please go ahead.
Thank you again. Well, maybe I'm overestimating the ease with which you can engineer your systems, but it would be also interesting to see how fragile is that fragile topology when you don't have an exact C2 symmetry, but for example, you move that center to the left or to the right. or what happens if instead of having C2, you introduce something which has C4 instead? Or, you know,
no, these are all very interesting questions. Like C4, in this case, if you do a C4 symmetric cut, it will be all fine. Well, one will actually need to measure, but we expect it to be all fine because C2 is the real protecting symmetry of this platform. If you extend it to C4, you're still protected by C2 because it's a subgroup of the full P4ML. Imperfect cuts is a good question. We actually didn't study it. You could simulate it. Realizing all this kind of experiment has some overhead. At some point, one needs to stop because you saw each value of lambda is a whole new central piece of the sample. It's a huge sample. It actually surprisingly requires quite some precision in the 3D printing. So there are only certain 3D printing technologies that can produce it. Yeah, we didn't feel like 3D printing further pieces to prove this. I think, you see, I don't expect to have dramatic effect, meaning let's take this C2 cut not be exactly C2 symmetric, which it's actually possible in our system. So what you will have is that the crossing between the even and odd state will not be protected anymore. So we'll open a small gap, exactly as you open the small gaps in the edge state of crystalline topological insulator. So that's true. I think that would be, though, not observable in the experiment because I expect a small gap or a gap proportional to how much you break C2. But there are other interesting questions that can be explored. For example, there has been proposal afterwards that disclination actually bounds charge or bounds mode in fragile topological insulator. So a nice interesting thing would also be taking our sample and create a disclination and see whether we get a bound mode there. I actually think we are just at the beginning of exploring these fragile topological insulators. And yeah, I don't think it's a fully settled what are the whole set of robust features associated to it. Or whether the robust one is not robust.
So I fully appreciate the fundamental meaning of your research, and I think it's very fascinating, but it would be an extra question. Do you think that can be somehow used? Apart from giving us, the sense of wonder at the beauty of nature.
So I think one needs to define used, meaning I'm a theoretician again. So for me, the use is like, I love being able to just run to the lab and turn the theoretical ideas into actual data, experimental data. So that for me, it's a use. Like proving theoretical ideas as much as cold atoms is a use. If we define use as the greater population will benefit from it because we will implement in the technology, this acoustic gigantic sample, I can almost certainly say no. Some microscopic elastic sample, I do have a hope, meaning, for example, the high order topological insulator where you have this sample, a square, and you come with an ultrasound, and instead of vibrating the whole sample, vibrates only the corner, so you localize your excitation. Maybe some application for sensing, possible. If you manage to engineer some robust edge states, then why not? Because you see, now we are in the electronic era where everything is electronic, but electronic is dissipative and consumes a lot of energy. There are some niche applications where a mechanical realization of wave guiding or transmission will actually be beneficial. Absolutely an open question whether this should be topological or not. But I think this is an open question also in the electronic domain, whether defect line cannot guide the electrons. Like whether we really have topological protection that we can benefit in a real world application. I think it's an open game also in the electronic community.
I would say also in photonics, it's the same. There are thousands of proposals.
No, absolutely. No, photonics, yeah, that's probably my scene. When I talk about metamaterial, I include everybody. I include elastic, acoustic, photonics. I took very broadly.
So thank you for answering the questions and for the very nice talk. I really enjoyed it.
Thanks. Thank you very much.
Thanks.
I have a question myself regarding the supplementary materials of the science paper, where at some point you show a cut where you show how the H mode of the system are moving through the gap.
Opa.
And I'd always, yes, exactly. I always had the impression that this was related to the line cut that you do in the center of the system,
No,
but today I had the impression that actually has nothing to do with that.
Yeah, it has nothing conceptually, something practically. Meaning, as we were discussing before the talk, these platforms actually was proposed in terms of this pincher number. So you can introduce this pincher number that's sketched with this horrible formula below. So you do expect edge states, but the pincher number doesn't have a well-defined boundary correspondence, meaning you can close at the edge either the energetic gap or the spin gap. And if you close the spin gap, you don't have edge modes. So we want a fully isolating system, so we don't want things crowding the bulk. So we need to get rid of the edge modes, and that's what this perturbation that couples the two bilayer in a straight way do. It attaches the edge modes.
But then actually, where is this perturbation applied?
Right. So in a pristine sample, it's on the edge of the sample, of the whole sample.
Okay. So on the perimeter.
Right. When you start doing the lambda cut, that's effectively, especially when lambda equal to 0, you're introducing a new boundary there effectively.
Mm-hmm.
So
the idea is that you do this cut along the perimeter so that you get rid out of the boundary modes. And right. Then along the yellow cut, you get this extra spectral flux due to the...
Exactly. So if you look at here, this picture closely, you see that there are these coupling are direct from bilayer to bilayer on the 2C side.
Okay.
So on this side, you see on the cut, we have them to get rid a bit of these edge modes.
But is this now the center or the boundary?
This is
on the boundary.
The center. So it's here. It's
okay, but you told me before that you do this coupling between the lower and the upper layer for removing the edge state only along the perimeter.
No, first at the perimeter.
Yes.
That's the pristine sample without twisting boundary. And when we twist boundaries, we're effectively introducing an extra edge on your sample.
So for the center, you do all along this pink region.
Exactly, along the cut, as you see here.
I see. Okay.
And you see what you do, you're moving this edge state from disconnected from the upper band, you move them to the lower band.
Okay.
That's exactly why I said that we don't have only one state flowing. Because the moment you do this edge, this cut, you're introducing a new edge. So you have all these edge modes flowing from the upper band to the lower band. That's a simulating cut of our sample. What we see in our experiment is a blurred mode that goes. But among this mode, there is only one that actually is the first that is localized at the center, and the other are delocalized along the line. And again, how do you confirm that? Is that you measure, this is simulation, so you can have full access at all states. You measure how many even and odd states you have in the occupied band, in the bulk band. And here you see the delta index, so here is delta 1. The moment this state touches, delta changes sign. And then all these extra states that come in actually have the same number of even and odd states. So they are not the state associated with your topological index, they're just these disturbance edge modes that are coming in.
That in principle you can never completely remove.
Right, you can move them in the bulk band, and the only thing you can do, you can move from the edge state, so you can fully move them in one of the two bulk bands.
Okay.
But the moment states flowing from one back to the other, you get them flowing too. That's why a posteriori, I would probably spend more time thinking about a different model to realize these fragile effects.
And then being that this is a theoretical result, you can also check where those modes are sitting, and probably are just sitting on the top and on the bottom of the sample, right?
Well, these disperse along the line, along the cut. This is localized in the symmetry center.
Okay.
This is the one that you care about. This actually is interesting. It's a corner mode. This is actually a mode localized in the corner. Because, well, you do expect corner modes, you don't have chiral symmetries.
And again, could you go one slide back? So now, clearly, in the theory, you can use this lambda is a numerical parameter. But
no, actually no. No. Also here, no, because this is theory not type binding, but finite element simulations.
Okay, so you have to redesign the sample, so to say.
Yeah.
Exactly as you do in the experiment.
Exactly. This is exactly the experiment if you want.
I see. Okay, because this is something that really, reading the article, I didn't grasp that each lambda corresponds to a different sample.
Right. It's a bit too hidden. The only way you can realize it is at the beginning where you describe the material, there is a whole table where there are different Vero white, Vero pink, Vero blue, and these are they have associated the corresponding
to
percentage of a closure. Yes, they have this number associated to them. And you see this stupid figure, the colors, these are all the different kinds.
Yes, I see. Well, this figure is missing in the article.
Yeah, I don't think that, we sometimes we hide legal figure in the article. They don't like it because of copyright issue. So
I thought you want to ask something? Yes. So I have one remaining question that came well, yeah. But this is not a fragile question. So it's a related but not completely related question. So have you envisioned or have you done any experiments on an acoustic system to realize a charm insulator? So what would be a magnetic field in an acoustic system if the answer is yes? Or have you thought about it?
No, we didn't. Romain Fleury, now at ETHzürich, did it. What you do, what they did there is you need to have an active controller on it. So essentially, let's imagine a 3-junction with channels and the site here. What it does is it has a circulator, if you want. It has an active airflow that induces a chirality, so you break time reversal symmetry. But you, in this approach, you open a very small gap. We just a tube below the flow. So here you add a fan, literally a fan on each side. Huge pump from below of air. This fan turns. You break time reversal symmetry.
And you have an object inside that hole or something like that?
Literally a fan, like a ventilator.
Ah, okay. Vale.
The problem is that it opens a very, very small gap. To open a huge gap, you will need this ventilator to go to an unbearable speed. That's the only way you can break time reversal. You need active control on it. If you have active control, the good thing is that you can actually do a different kind of magnetic field, a different gauge field. We did it in this vial system. You can do it. It's the same idea of gauge fields in graphene. You use strain. So you can do gauge field in acoustic with strain, but those don't break time reversal symmetry. That's why charm insulator, they really require an active control of your platform.
Yeah, but I assume that you get 5 points because of this strain.
No, we get rid of the vial points are there because actually vial points is the dream, because those, well, first of all, you don't have spin degeneracy, so they're all vial. You have no direct point, you have no four-fold degeneracy. And this crossing in the bands, it's easy to get. It's a bit harder to get them at the equal spacing, at the equal frequency. What you do with this gauge field, you actually induce Landau quantization. So you gap out the vial system, you get Landau levels, and in a vial system, the zero Landau level is dispersing along the field. And now if you have magnetic field, they disperse in opposite direction, the two vial points. With this kind of strain field, called axial field, they disperse in the same direction.
Okay, thank you very much.
So I think we can close the session here. If we have more questions for Valerio, you can easily find his email on the web and you can question him more. And thank you all for attending the talk, and thanks Valerio again, and good luck with the pandemic in Switzerland.
Thanks, you too.
I close the session.